Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So for part number 3, we will discuss about the actual vapor power cycle or the actual Rankine cycle. Okay, when we discuss about the actual vapor power cycle or actual Rankine cycle, we need to consider the factor of irreversibilities, such as the fluid friction throughout the piping line in the steam power plant, and this effect will cause pressure drop during the process, such as in the heat addition process and also heat rejection process. And the second one, the irreversibility factors such as the heat losses to the surrounding, and this effect, the second effect, will cause the temperature drop throughout the process. So this irreversibility factor will cause the reduction of thermal efficiency for the Rankine cycle, where due to the factors, the value pumped in that we need to supply to the actual Rankine cycle will be increased. Similarly to the amount of heat addition that we need to supply during heat addition process also will be increased. However, the amount of W out that produced by the turbine during the expansion process will reduce. So this effect will reduce the overall efficiency of the steam power plant. Okay, so this figure shows the TS diagram in order to show the difference between the ideal Rankine cycle and also the actual Rankine cycle. So the ideal Rankine cycle shown in this TS diagram present by the red color line cycle. Okay, start from state number 1 prime, 2 prime, 3 prime, and also 4 prime. And the second cycle that's shown by the what we call black color dash line cycle is the cycle for the actual Rankine cycle. So we can see here the difference between the ideal Rankine cycle and also the actual Rankine cycle. So here, during the compression process in the pump, you can see due to the irreversibility in the pump, the process of the compression will be non-isentropic, as shown by process from state number 1 to state number 2. Similarly to the turbine, okay, due to the irreversibility that we discussed before in the turbine, so we will have the expansion process will not isentropic process. Okay, so for the pump we need to supply more W in. For the actual cycle, for the turbine, the amount of W out produced will be less compared to the ideal Rankine cycle. Okay, so during heat addition process in the boiler, start from state number 2 to state number 3, we can see that there are a pressure drop in the boiler during the process, as shown in the TS diagram. Similarly, in the condenser, we will have pressure drop in the condenser when we consider the irreversibility factor. However, the simplest case for the actual Rankine cycle or actual vapor power cycle is shown in this TS diagram. So if you look at the ideal Rankine cycle, so we will have the cycle that represented by the red continuous red color line cycle. So we will have state number 1, state 2s to represent the isentropic compression, state number 3, and also state number 4s that represent what I call the isentropic expansion process in the turbine. So at the pump, we will have W in. At the turbine, we will have W out. At the boiler, we need to supply Q in, and at the condenser, we need to release heat Q out. Okay, so for the simplest case of the actual Rankine cycle, the pressure during heat addition process and also heat rejection process still constant. Okay, so now the difference is we will have what I call the increase of W in at the in the pump for the actual compression, and the outlet condition for the actual cycle is state 2A. Similarly to the turbine, the what I call the amount of W out in the actual cycle will be lower than the ideal ranking cycle, and the outlet condition is represented by state number 4a. Okay, so now in order to describe the what I call the process, the actual process of the compression and also actual process of the turbine expansion process, okay, we need to consider isentropic efficiency. So for the ideal case, for the compression and also expansion, isentropic efficiency is 100%. However, for the actual one, the value of isentropic efficiency for the pump and also for the turbine will be lower than 100%. So in order to determine the isentropic efficiency for the pump, mu P equal to W in for the ideal process divided by W in for the actual process, also equal to H2S minus H1 divided by H2A minus H1. However, for the turbine, the isentropic efficiency for the turbine mu T equal to W out actual divided by W out ideal equal to H3 minus H4A divided by H3 minus H4S. And then we need to recalculate, if we consider the isentropic efficiency, we need to recalculate the thermal efficiency for the actual Rankine cycle. Example 4.2, a steam power plant operates on the cycle shown in the figure. If the isentropic efficiency of the turbine is 87% and the isentropic efficiency of the pump is 85%, determine A, the thermal efficiency of the cycle, and B, the net power output of the plant for a mass flow rate of 15 kg per second. So this is the figure. So we have 6 states involved. State number 1, 9 kilopascal at 38 degrees Celsius. State number 2, 16 megapascal. State number 3, 15.9 megapascal at 35 degrees Celsius. State number 4, 15.2 megapascal at 625 degrees Celsius. State number 5, 15 megapascal at 600 degrees Celsius. And state number 6 at 10 kilopascal. The efficiency, the isentropic efficiency for the pump, mu P equal to 0.85, and isentropic efficiency for the turbine, mu T equal to 0.87. So now you need to determine the thermal efficiency and also the net power output for the steam power plant. Okay, determine A, the thermal efficiency of the cycle. So in order to determine the efficiency of the cycle, you can use this formula, the general formula for thermal efficiency, where mu TH equal to W net divided by Q in equal to 1 minus Q out divided by Q in. And we know that W net also equal to Q in minus Q out, also equal to W out minus W in. Okay, the data given based on the figures. So we have P1 equal to 9 kilopascal, T1 equal to 38 degrees Celsius, P2 equal to 16 megapascal, T2 unknown, P3 equal to 15.9 megapascal, T3 equal to 35 degrees Celsius, P4 equal to 15.2 megapascal, T4 equal to 625 degrees Celsius, P5 equal to 15 megapascal, and T5 equal to 600 degrees Celsius. And the last one, P6 equal to 10 kilopascal, and T6 is unknown. And the isentropic efficiency for the turbine given in the question is equal to 0.87, and for the pump is equal to 0.85. Okay, so now in order to answer the question involved with steam power plant or Rankine cycle, so first what we have to do, we need to determine for each state involved, we need to find out the important parameter for the steam power plant for each state, especially the value of enthalpy, entropy, and so on. Okay, first for state number 1. So as I mentioned before, for water table, in order to determine the other properties for each state, at least we need to have 2 information in order to use the thermodynamic table for the water. Okay, for state number 1, so we already have 2 data, P1 equal to 9 kilopascal and T1 equal to 38 degrees Celsius. So next we need to determine the phase or the condition of state number 1. whether the compressed liquid, saturated mixture, or superheated vapor. First, in order to determine the phase, we need to refer to the saturated water table based on pressure table. So by referring to the value of P19 kilopascal, we need to determine the T saturated temperature at that temperature. So now we need to make interpolation to determine the value of T saturated. So now we need to make interpolation for 9 kilopascal in order to determine the value of T saturated at state number 1. So from the interpolation, we obtain that T saturated at 9 kilopascal is equal to 45.22 degrees Celsius. And then we compare the saturated temperature with the temperature given T1 equal to 38 degrees Celsius. So T1 lower than T saturated at 9 kilopascal. Thus, the phase of the state number 1 is in compressed liquid region. So now, because the minimum data for compressed liquid table is 5 megapascal, for state number 1 the pressure is 9 kilopascal, so the data is not available if you refer to the compressed liquid table. Thus, we need to make assumption. So the closest phase to the compressed liquid, which is still 100% liquid, is the saturated liquid. So we assume that the state number 1 is in saturated liquid condition, where 100% of water in liquid form. Thus, we need to refer to the saturated water table, and because we make assumption, we need to base on the saturated water table based on the temperature. Okay, so we need to make interpolation to determine the data or the important information for the temperature of 38 degrees Celsius. So from the table, we can determine the value of V1, where V1 equal to Vf at 38 degrees Celsius equal to 0.001007 meter cubic per kg. We can also determine the value of H1, where H1 equal to Hf at 38 degrees Celsius equal to 159.21 kJ per kg. Okay, and also we can determine the value of S1. S1 equal to Sf at 38 degrees Celsius equal to 0.5456 kJ kg Kelvin. So we need to determine the entropy, because later on maybe we can manipulate the value S1 for isentropic process in order to determine the other value for different state, for the other states, especially for state number 2. Okay, for state number 2, so we have two types of state number 2. So we have state 2s for the ideal compression process, and second one we have state 2a for the actual compression process in the pump. Okay, for state 2s, we can use a compressed liquid table, because in order to use the compressed liquid table, the pressure must be greater than 5 megapascal. So you can see that P2S, P2A, the pressure will be the same at 16 megapascal. So P2S equal to 16 megapascal, the pressure greater than 5 megapascal. So we can use the compressed liquid table. And the value of entropy S2S equal to S1 due to the isentropic process for the ideal case equal to 0.5456 kJ per kg Kelvin. And now we can we already have two data, so we can refer to the compressed liquid table. So the table shows the compressed liquid table for pressure of 15 megapascal and also 20 megapascal, and the data of enthalpy, entropy, density, and also internal energy for the temperature of 20 degrees Celsius and also 40 degrees Celsius. However, in this table we don't have direct value in terms of enthalpy, entropy for 16 megapascal. So now what we have to do, because data is not available for 16 megapascal, so now we need to create the table for 16 megapascal. Okay, so we need to create our own table for 16 megapascal. So now we need to extract data in terms of enthalpy and also entropy for pressure of 15 megapascal and also 20 megapascal at temperature of 20 degrees Celsius. Okay, as shown in the table. So the table shows the different value of pressure and also enthalpy value and entropy value for constant temperature of 20 degrees Celsius. So by using interpolation, we can determine the enthalpy and also entropy value for 16 megapascal. Okay, the value of enthalpy and also entropy at pressure of 16 megapascal. Okay, and also we need to extract the data in terms of enthalpy and entropy at pressure of 15 megapascal and also 20 megapascal for temperature at 40 degrees Celsius. Okay, so now the second table shows the what I call the data, okay, in terms of enthalpy and also entropy at different pressure for the temperature condition at 40 degrees Celsius. Okay, by using the interpolation, so we can determine the value of enthalpy and also entropy at 16 megapascal with the temperature of 40 degrees Celsius. Okay, so now we already have the data for the pressure of 60 megapascal in terms of enthalpy and also entropy. So we rearrange the data. So now we already obtain the data in terms of enthalpy and also entropy for 60 megapascal. Okay, by using the value of S2S, we can interpolate the value of enthalpy by using the data of entropy and also enthalpy for the pressure of 16 megapascal. Okay, so after interpolation, we obtain that H2S equal to 175.4 kilojoule per kg. Okay, that's how we create our own table and also determine the value of H2S in this example. Okay, so next for state 2A, because we don't have enough information for state 2A, so we know that state 2A is in compressed liquid. But in order to determine the enthalpy for H2A and the enthalpy for state number 2A, which is referred to H2A, so we can use the isentropic efficiency equation for the pump. Okay, so you need to determine H2A by using this equation. So we know that isentropic efficiency for the pump equal to H2S minus H1 divided by H2A minus H1. So the isentropic efficiency value already given in the equation. H1, H2S we already determined. So now rearrange the equation, we can obtain the value of H2A, where H2A equal to 178.26 kilojoule per kg. Okay, for state number 3, the condition at the inlet of the boiler. So we already have two information here, where P3 equal to 15.9 megapascal, T3 equal to 35 degrees Celsius. So the data, we already enough data to use the water table. However, we need to determine the phase of the water first at the inlet of the boiler. So as usual, we need to refer to the saturated water table based on pressure table and determine the what I call the saturated temperature for the pressure of 15.9 megapascal. Okay, by using the table, so we need to make interpolation. So the value of T saturated at 15.9 megapascal is equal to 346.92 degrees Celsius, and compare with the value of T3 at 35 degrees Celsius. So the temperature of T3 is lower than T saturated at 15.9 megapascal, which means that the phase for state number 3 is in a compressed liquid phase. Okay, because the pressure is greater than 5 megapascal, so we can obtain the data for state number 3 by using the compressed liquid table. However, we don't have direct table for 15.9 megapascal, so again we need to make our own table for 15.9 megapascal. Okay, So by referring to the temperature of 35 degrees Celsius is in between 20 degrees Celsius and also 40 degrees Celsius. So now we need to refer the data in terms of enthalpy and also entropy for temperature of 20 and also 40 degrees Celsius at pressure of 15 megapascal and also 20 megapascal. So now by referring to the table, we can extract data in terms of enthalpy for 50 megapascal and also enthalpy for 20 megapascal at temperature of 20 degrees Celsius and also 40 degrees Celsius. So we arrange the data, so we will obtain what I call the value of 35 degrees Celsius by interpolation between the value of temperature and also enthalpy for 50 megapascal. So we will obtain the value of enthalpy at 35 degrees Celsius for 15 megapascal. And then by using the what I call enthalpy value at 20 megapascal for temperature of 20 degrees Celsius and also 40 degrees Celsius, and we have to make interpolation to obtain data in terms of enthalpy for 35 degrees Celsius at 20 megapascal, and interpolation between the temperature value and also the enthalpy value. So we will obtain the enthalpy value at 35 degrees Celsius for 20 megapascal. So rearrange the data into one table, the table for temperature and also the pressure. So from this table we can make interpolation between the pressure value and also the enthalpy value at 35 degrees Celsius. Okay, because we already determined the enthalpy value for 35 degrees Celsius for the pressure of 50 megapascal and also 20 megapascal. So now by using the interpolation, we can determine what I call the value of enthalpy at 15.9 megapascal at temperature of 35 degrees Celsius. So the value of H3 will be equal to 160.86 kJ per kg. Okay, for state 4, as we discussed before, the state number 4 actually same as the state number 2, where we have two type of state 4, state 4A and also state 4S. However, for this problem, we already obtained the data for state 4 for the actual one, state 4A, so no need to determine state 4S during the calculation. Okay, so the condition for state 4S, P4 equal to 15.2 megapascal and T4 equal to 625 degrees Celsius. First, determine the phase for state number 4A by using saturated water pressure table. So we need to make interpolation to determine the saturated temperature at 15.2 megapascal. So T saturated at 15.2 megapascal equal to 343.28 degrees Celsius. Compare with the temperature given, T4 equals 625 degrees Celsius. So T4 greater than T saturated at 15.2 megapascal, which means the phase of state number 4A is in superheated vapor region. So now we need to consider superheated water table. Okay, so similar with the previous state, we don't have direct table for 15.2 megapascal. So now we need to create our own data or our own table for 15.2 megapascal. Okay, so now we need to refer to the data for pressure at 15 megapascal and also 17.5 megapascal. Because T4 equal to 625 degrees Celsius, so we need to refer to the temperature in the table at 600 degrees Celsius and also 650 degrees Celsius. So we need to extract data into enthalpy at 15 megapascal and also enthalpy at 17.5 megapascal. So extract the data, so we can obtain the table for 15 megapascal in terms of enthalpy and also temperature. So make interpolation, so we will obtain the enthalpy value at temperature of 6 to 5 degrees Celsius for the pressure of 15 megapascal. And then extract the data into enthalpy and also the temperature for the pressure of 17.5 megapascal and we need to make interpolation to determine the enthalpy value at temperature of 6 to 5 degrees Celsius. Okay, and rearrange the data. So now we already have the new table in terms of temperature, pressure, and also enthalpy value. So we already determined the enthalpy value at temperature of 6 to 5 degrees Celsius for 15 megapascal and also 17.5 megapascal. So now by using interpolation, we can determine the enthalpy value at 6 to 5 degrees Celsius for pressure of 15.2 megapascal. Okay, so the value of enthalpy for state 4A, which is referred to H4A, equal to 3645.68 kilojoule per kg. Okay, so that's how we determine what I call the enthalpy value for the state number 4A. Okay, state number 5, the condition at the inlet of the turbine. So the data given where P5 equal to 50 megapascal, T5 equal to 600 degrees Celsius. So we already have two data. So in order to determine the phase, we need to use saturated water table based on pressure, where at 50 megapascal, T saturated is 342.24 degrees Celsius compared with T5 value. So T5, which is equal to 600 degrees Celsius, greater than T saturated at 15 megapascal. So the phase will be superheated vapor. So now refer to superheated water table at 600 degrees Celsius and 15 megapascal. So we can determine the value of enthalpy, where H5 equal to 3582.3 kilojoule per kg. And also we can determine the value of S5, where S5 equal to 6.6776 kilojoule per kg Kelvin. So later on we will manipulate the value of entropy S5 during the isentropic process to determine the information for state number 6. Okay, for state number 6, so we have two states involved, state 6S and also state 6A. Okay, now for state 6S, we know that the state involved with isentropic process. So the pressure given for state 6, P6 equal to 10 kilopascal, and this pressure also same as the pressure for state 6A. And due to the isentropic process, S6S equal to S5 equal to 6.6776 kilojoule per kg Kelvin. Okay, so now we need to determine the phase for state S. So previously, in order to compare or in order to make comparison to determine the phase, we use the temperature, pressure, and also the saturated temperature. However, here we need to we only have the data for pressure and also entropy. So in order to determine the enthalpy, to determine the phase, we need to refer to the enthalpy value S6S, and also we need to refer to the value of SF and also SG at 10 kilopascal by using saturated water table based on pressure. So here at 10 kilopascal, the value of SF equal to 0.6493 kilojoule per kg Kelvin, and SG equal to 8.1502 kilojoule kg Kelvin. So if the value of S at the state number 6S greater than SG, so the phase will be superheated. But if the value of S6S is in between SF and also SG, the phase will be saturated mixture. Okay, so now if you compare the value, so S6S will be in between SF and also SG value. So the phase will be saturated mixture. So for saturated mixture region, the value of enthalpy we cannot obtain directly from the table or by using the interpolation. But so now for saturated mixture, the enthalpy value we can determine by using the equation. So now first we need to manipulate, we need to determine the value of X, the steam quality for state 6S, by manipulating the equation for entropy, where X6S equal to S6S minus SF at 10 kilopascal divided by SFG at 10 kilopascal. So the value of SF and also SFG at 10 kilopascal we can determine from saturated water table at 10 kilopascal. substitute all the value from table, so we can determine that the quality of steam at state 6S equal to 0.8037, which is equal to 80.37%. So now, in order to determine enthalpy at state 6S, use the enthalpy equation where H6S equal to HF at 10 kPa plus X6S multiplied by HFG at 10 kPa. So the value of HF and also HFG at 10 kPa you can determine from the saturated water table at 10 kPa. Substitute the value. So the enthalpy value for state 6S will be equal to 2115.0 kJ per kg. Okay, for example 4.2, this example involves the actual Rankine cycle. So the calculation for this problem, we need to consider the actual data for the actual states. So now for state 6, we also need to consider state 6A. Okay, so we cannot obtain direct value in terms of enthalpy for state 6A from the table. So now we need to manipulate the equation for the isentropic efficiency for the turbine, where mu T equal to H5 minus H6A divided by H5 minus H6S. So H5, H6S we already determined from the previous state, and the value of isentropic efficiency for the turbine already given in the equation. So now we can determine the value of H6A. So rearrange the equation. So H6A equal to 2305.75 kJ per kg. Okay, so we already obtained all the value in terms of enthalpy for each state. So now we can calculate the W out actual at the turbine, where W out actual equal to H5 minus H6A. Substitute the value of H5 and also H6A. So we will obtain W actual out equal to 1276.55 kJ per kg. And also we can determine W actual in for the pump equal to H2A minus H1. Substitute the value of H2A and also H1 into the equation. So WA in for the pump equal to 19.05 kJ per kg. Okay, so we know that W net actual equal to W out actual minus W in actual. Okay, so W net actual will be 1257.5 kJ per kg. So in order to determine thermal efficiency, we also need to calculate the value of Q in. So now we need to refer to the formula for Q in based on this diagram, where Q in equal to H for A minus H3. Substitute the value. So Q in will be equal to 3484.82 kJ per kg. And we know that the thermal efficiency equal to W net divided by Q in. So in this case, thermal efficiency equal to W net actual divided by Q in actual. Substitute the value. So the thermal efficiency for this actual Rankine cycle equal to 0.3608 or 36.08%. Okay, question B. Determine the net power output of the plant for a mass flow rate of 15 kg per second. So the value of 15 kg per second represents the value of m dot. So we know that we already calculate that W net actual equal to 1257.5 kJ per kg. So this value actually refer to the specific W net for the actual process. So in order to determine the net power output, we know that m dot equals 15 kg per second. We just multiply the mass flow rate with W net actual that we already calculate. So the net power output, which is equal to W net actual dot equal to m dot multiplied by W net actual, which is equal to 15 times 1257.5 equal to 18.862 megawatt. Okay, so this is the value for the net power output for the actual Rankine cycle, for this actual steam power plant cycle. Okay, let's say the question asks you to draw the complete TS diagram. So what you have to do, so you need to draw the TS axis and also the saturation line. And then you need to draw all the constant pressure line involved in the equation. Okay, so we have constant pressure line for 9 kilopascal, 10 kilopascal, 15 megapascal, 15.2 megapascal, 15.9 megapascal, and also 16 megapascal. Okay, so then you need to determine the saturated temperature for each constant pressure line, as we already calculate in previous slide. Okay, and then you need to plot what I call the specific state by referring to the temperature given. Okay, so because we know that the temperature for state number 1 is 38 degrees Celsius and the phase is compressed liquid, because the temperature is below than its saturated temperature. So the state number 1 must be below than what we call temperature of saturated temperature at 45.22 degrees Celsius. And then we know that after the compression, the phase for state number 2 must be in compressed liquid, and for state 2s the process must be isentropic. By drawing the vertical line intersect with the pressure of 60 megapascal, we can determine state 2s on the TS diagram. And for 2a, state 2a, although we don't have in terms of temperature, but we know that what I call the state 2a is located on the same constant pressure line, same as state 2s, which is 16 megapascal. And we know that the state 2a must be beside the state 2s, and the value in terms of enthalpy will be greater, because we know that for the actual process, W in will be greater for the actual process compared to the ideal compression process. For state 3, so the pressure slightly dropped at 15.9 megapascal, and we know that the temperature given is 35 degrees Celsius, and the point must be located at lower than the saturated temperature for the 9 kilopascal as shown in the slide. Okay. For state number 4, we already know that the temperature is 6 to 5 degrees Celsius and the pressure is 15.2 megapascal. So easily we can plot the point for state number 4, and the point must be greater than the T saturated of pressure 60 megapascal, because the saturated temperature for 60 megapascal is equal to 347.44 degrees Celsius. And then we have the inlet of the turbine, state number 5. The temperature is 600 degrees Celsius, so we just plot, try to find intersection point between 600 degrees Celsius and also 15 megapascal. Okay, the temperature must be greater than 347.44 degrees Celsius. So the location for the state number 5 must be higher than this temperature. And for state number 6, so we can determine easily for state 6s, where the intersection will be at 10 kilopascal constant pressure line. So from state number 5, we just draw the vertical line, so we get state 6s. For state 6a and also state 6s located on the same constant pressure line of 10 kilopascal. Okay, so because we know that during our calculation state 6s is in saturated mixture region, we just plot we just put the point for 6a slightly to the right from the point of 6s. Okay, so now we can connect all the points accordingly. Okay, so this is our actual Rankine cycle, okay, TS diagram. Okay, so that's all I think the solution for example 4.2.